Welcome back to the Explainer. Today is the day. We are diving into the ultimate capstone of the GD&T Master Course. We're going to take everything we've learned about the ASME Y14.5 2018 standard and really see how it bridges that massive critical gap between an abstract design on your computer screen and the actual physical manufacturing reality on the shop floor. It's time to put it all together. All right, here is our blueprint to reality for today. We'll start with the high stakes of poor GD&T, run through a quick core concepts review, dive into a real drawing analysis, look at some common errors, and finally wrap up with verification. Part 1. The stakes of poor GD&T. So before we put on our manufacturing engineer hats, let's take a second to really ground all this math in reality. Misinterpreting these symbols, it isn't just some minor academic mistake. It has massive, sometimes terrifying financial and safety consequences. Think about it. A failed solid-state drive assembly can cost a company literal millions of dollars in high-volume production. Or worse, imagine a horribly misaligned Score International racing roll cage that causes severe structural weakness. The consequences of misapplied tolerances are incredibly severe. GD&T is the fundamental language that ensures our parts actually fit and, more importantly, function safely. Let's move into Part 2, Mastering Core GD&T Concepts in a Unified Framework. Just as a really quick review, remember that absolutely every single geometric characteristic symbol you will ever put on your print falls neatly into one of 5 functional control categories. We're talking form, profile, orientation, location, and runout. Form controls the basic shape of individual features, orientation obviously controls your angles, location tells you where a feature is, profile controls those complex 3D surfaces, and runout controls a feature's relationship to a rotating axis. Keeping these 5 buckets categorized in your head honestly simplifies the entire standard. Now, going beyond just the symbols, applying the right material condition modifier is absolutely essential. Knowing when to use which modifier is really the secret sauce here. Maximum material condition, or MMC, is basically a machinist's best friend for clearance fits. Why? Because it creates that incredibly valuable bonus tolerance while still guaranteeing a fully functional part. Then you have least material condition, LMC, which is vital when you're trying to preserve, say, a minimum wall thickness. And of course, regardless of feature size, RFS, that's just our default when no specific material condition is required for the part to actually function. Which brings us to Part 3, Drawing Analysis and our Capstone Blueprint. Okay, let's step into the shoes of a senior manufacturing engineer for a minute. When we're staring at a real-world production blueprint, our absolute first non-negotiable step is establishing the datum reference frame. We have to identify those primary, secondary, and tertiary datums. And remember, these aren't just arbitrary letters slapped on a page. They are the physical foundations that constrain our part's 6 degrees of freedom out there in space. The primary datum gives us our initial physical contact, usually a nice, large, flat surface. Then the secondary and tertiary datums lock in the rest of the rotation and translation. This is exactly what dictates our entire work-holding strategy when we get to the CNC machine. So, building off those datums, the feature control frames step in to dictate our actual physical verification strategy. See, GD&T isn't just about drawing fancy boxes on a screen. It's about translating those abstract symbols into hard physical reality. For instance, a position callout actually translates directly into a simulated ring gauge. Or take a datum A-plane. That creates a tolerance zone of 2 perfectly parallel planes exactly 0.030 apart. This is exactly how your precise design intent gets communicated to the quality inspector down the line. It's like a universal translator. On to Part 4, Avoiding GD&T Errors and Navigating Common Industry Pitfalls. Listen, even if you have a literally perfect design on paper, incredibly costly mistakes still happen on the shop floor. You really need to ask yourself this every single time you review a print. Are my tolerances functional, or are they just safe? A massive pitfall in this industry is overcomplicating designs with excessively tight, totally unnecessary dimensions just because an engineer wanted to play it safe. Honestly, that's a rookie mistake that absolutely skyrockets manufacturing costs and ruins lead times. You absolutely have to balance the ideal world of product design with the gritty, real world of manufacturing and assembly. Functional tolerancing means you are only applying those super tight tolerances where they are genuinely crucial to the assembly's fit or performance. Everything else, it should be as loose as functionally possible. That reduces scrap rates and it keeps your costs down. Bottom line, do not over-constrain your non-critical features. It's just not worth it.
Some other really frequent errors include mixing up those material condition modifiers we just talked about, or, and this is a big one, completely ignoring tolerance stack-up effects across multiple chain dimensions. There's this classic example in engineering education about first-year undergrads trying to build a steam engine. They constantly confused flatness, which is a form control that requires 0 datums, with parallelism, which is an orientation control that absolutely must have a datum reference. That one simple mix-up, it inevitably leads to misaligned mating components and a complete functional defect. It's a small error with a huge ripple effect.
And finally, Part 5, Inspection Strategies and Proving the part actually matches the print. Ultimately, right, a brilliant design is only as good as our ability to actually inspect it. Modern verification heavily relies on intelligent, model-based metrology software, and the workflow is just fascinating. First, we open up the 3D CAD model, which already has all that intelligent GD&T data baked right in. Second, we create an automated programmable inspection plan. Third, we tell the software to align the physical part by setting the datum targets we established earlier. And finally, we just run the routine using a coordinate measuring machine, a CMM, or a 3D scanner. This automated CMM strategy gives us an immediate pass or fail deviation report right there on the screen. It perfectly overlays the physical geometry against your prescribed GD&T allowances, showing the exact deviations. And the absolute best part, it completely eliminates human data entry errors and all those tedious manual calculations. The loop from design to manufacturing to quality verification is completely 100% closed. As we wrap up this extensive curriculum, the source material leaves us with a very well-earned message. You have completed the GD&T Master Course based on ASME Y14.5-2018 R2024. I highly recommend you keep practicing with real manufacturing drawings and really dive into CMM metrology software on your own. But as you step out to design the future, I want to leave you with one final question to chew on. Next time you assign a tolerance to a feature, are you simply defining a dimension, or are you truly guaranteeing its real-world function? Keep learning, keep applying, and I'll see you in the next explainer.